And yeah, so welcome back to System Software. Let's go into our next section of the class, the second half of the class, where we talk about compilers. We're in the compilers foundation section, which is a little now broken up by the midterm because of class cancellations. But today I want to talk to you about how your source code, which is really just a text file, gets turned into a running program, a process on your machine. So to get started, let's answer some, kind of Merriam-Webster questions, although it's probably a different definition there. What's a program? In the kind of architecture, you took computer org. What's an yeah. Oh, did you raise your hand? Oh, sorry. Okay. You.
Abstraction.
What's that?
Abstraction.
An abstraction. A program is an abstraction.
We said like a running program.
Well, what's a program? A program, just a program. So yeah, we have the next question is going to be what's a running program or what's a process. But I think you were first. Yeah.
A set of instructions for the computer drawing.
Yeah, it's a set of instructions. So I think this is the computer org description, right? Don't they say this? It's like you have a stored program machine where it has some memory storing a set of instructions. So a program is really just a sequence of instructions to a machine. In the computer org world or in the processor world, that would be machine instructions. But when we write C, are we writing machine instructions that the processor will run? No, right? We're writing for a different machine and actually a kind of a virtual machine. So source code is written in a programming language that may not actually correspond to machine code one-to-one. All right, what's a process in our systems context? Yeah.
A running program.
A running program. So we have a program, which is a sequence of instructions, and then we have a running program, which we call a process. So the core thing I want to get across to you is how we go from this source code to a running program. And in order to understand that, we have to actually understand a little bit about how programming languages work. So if you have a C program, like your Hello World program, does your processor, most of you have an Intel processor, maybe some of you have an ARM processor, does that processor run C code? Who says yes? Who says no? Who doesn't know? Okay, good. So then you'll see today how this works. So to motivate this is typically how you run your C programs, right? You learned this in Intro to C or Computer Org. This is what you do to supposedly run your C program, right? So why are there two commands to run it? Why not just run hello.c? Yeah.
One compiles it and one executes it.
Good, yeah. One compiles it and one executes it. So GCC, if you're not already aware of this, GCC takes that source code and it turns it into a runnable program, a program that can be run on your system and your architecture. And what makes this process so kind of mind-warping is that, if you notice when we run this, what's GCC? GCC is a program too. So we have to run a program that somebody wrote, and that program takes your C code and turns it into a runnable program. So this is the confusing part this is what's sort of tricky about compilers, is that there's really three programs that you have to keep in mind at the same time. You've got your source program, your output program, and you have the compiler program itself, which is yet another program which needs to be written in some language, which then will do this translation for you. Okay, so there are two, yeah, go ahead.
So what turns GCC into a runnable program?
That's a good question. What turns GCC? So does anyone know what language GCC is written in? What's that? Okay, it could be written in assembly, it could be written in C. So GCC, as it currently stands, is written in C. So what translates GCC into a runnable program? GCC, right? GCC. So you get this kind of, this self-referential behavior in the compiler, which is one of the kind of fun and interesting parts about the compiler world. This is called the bootstrapping problem, where how do you compile a C program if you don't have a compiler yet? And one way to do it is you write a compiler first, a small compiler in assembly, that will do your translation, and then you can eventually rewrite that program, that assembly program, in your language. And so that way, you kind of need an initial program originally to compile your compiler. This also creates some security and trust issues as well. But okay, that's a good question. So GCC, current iteration, is written in C. Needs a C compiler to compile it. But okay, so let's look at how we actually write one of these programming language implementations. So there's two core techniques: compilers and interpreters. Anyone aware of the difference or some examples of them? Yeah.
Interpreters are basically who are very compilers. They basically read each line of code and repeat each line of code, while compilers compile or read the whole program and then execute the program. If that makes sense.
So yeah, so that's pretty close. So interpreters, yeah, that's right. So interpreters look at each line of the code and they execute it, or they simulate what the behavior of that line of code would be. Compilers don't actually run the whole program. They read the whole program in and translate it to another program. So compilers do no, in the strictest sense, compilers do no execution of the program. As you'll see if you take a compilers class, compilers will do some interpretation actually of the program, but if we kind of make this a hard boundary, compilers doing translation, and interpreters are simulating or emulating each line of code. Yeah.
Well, we said like /while that starts the interpreter.
Dot slash what?
Like while, like whenever you do it.
Okay, so that actually brings up another interesting question: is hello is a program? Yeah. So the .c program is being translated to hello, an executable, and then we run hello. So is hello, the hello executable, being compiled or interpreted or something else? Yeah.
Well, it's already in a binary file. It's basically a binary file, so that here reads it, or just
What reads it? What reads it?
reads it. I'm sorry. What I'm trying to say is like it's already a binary file, so the computer already knows what to do with that binary.
The computer knows. Yeah, right. So the process. So who runs the hello binary? What machine is running it?
The virtual machine?
What's that?
The virtual machine? Or can it be
Well, it could be a virtual machine, but if you don't have a virtual machine, and you were right there, you had it. Like, what's running it? Who's running the machine code on your machine? The processor, yeah, the machine, the processor, the CPU is what's taking those instructions. The compiler is producing a binary that has machine code instructions. If you remember from computer.org, I think you did MIPS at computer.org. So there's a physical processor that can read those commands in binary and execute them, give you the output of those commands. So in that sense, is hello, if you could only pick between compilers and interpreters, is hello being compiled or being interpreted? Interpreted. And who's doing the interpreting? The processor, the CPU. You can think of the CPU as a kind of interpreter of machine code. And it's the electrical engineers who design it so that it will give you the output that you want for the instructions that you have. Kind of makes sense? Okay. So let's diagram this out. So we're going to talk through this a little bit. Let's diagram this. This can hopefully give you a better sense of what's going on here. All right. So if we have that's right, this doesn't. All right, here's our CPU. Here's our compiler. Our compiler takes the source code, turns it into a binary, and then through processes that we'll talk about a little later, this hello machine code gets executed on the CPU, and then you get your output. So where's the input go? Does the compiler take, so let's say instead of hello world, it's myls, and we pass it a parameter. Does that parameter get passed in the compiler, or does it get passed in the machine? Machine, yeah. So This is a massive oversimplification. I/O in the systems world is a little bit more complicated, but you can think of the any input being passed via the machine. So in the command line terminal, this would be through your keyboard, and there's actually hardware that reads the signals from your keyboard, and the kernel will process that input for you. And similarly, the output is also managed by the machine. Not really the CPU, but by the machine and the CPU. Yeah?
So, that was just a question, like, where is the compiler? Is it kernel, or is this
So the compiler is above the kernel. This is not like a complete diagram of the system. I've made some dramatic oversimplifications here. But the compiler is just another program that you run. So it's, in a sense, it's kind of equal to hello. It's running on top of the kernel. Kernel is providing access to the hardware, so you're not able to directly control the CPU to tell it to run hello. The operating system is mediating this for you, but the compiler is also running on the CPU. So we could actually kind of enhance this diagram by showing the compiler running on the CPU and taking your hello program as input and producing a hello binary. That hello binary also gets run on the CPU. So it's going to be a little convoluted if I draw an arrow to the CPU because it's not really in the same step of execution. But then after you produce that program, it actually gets stored on disk. And later, after you compile it, you can execute it on the CPU and get your output. Does that make it a little clearer? So the compiler itself is a program also that's running on your machine.
like Eustace?
Like Eustace, exactly. So Eustace has some Intel architecture processor, and when you do /hello, the operating system will run fork and exec, and it'll copy those machine code instructions into memory, and the kernel will tell the CPU to start executing. It'll change the program counter to start executing those instructions from the machine code. All right, questions on compilation? And so as we pointed out, this step here is like interpretation. If you think of the CPU as an interpreter, the interpreter takes both the program code and the input simultaneously, and it executes each instruction. It simulates the output of each instruction of that program, and eventually produces whatever output you have for that program. Okay, questions on the compiler? Yeah.
Do all languages have the same compiler, or is it like a standard form of a compiler, or?
That's a good question, actually. So no, not strictly speaking, but and I'll show this next time. I have a diagram I can show from the LLVM world, but sort of modern industrial compiler design tries to support multiple languages in the compiler. So GCC, you can target multiple backends. You can target Intel or x86. You can target ARM. You can target Spark. I think they have a lot of targets you can generate, a lot of machine code you can generate, and it also has different front ends like C, C++, Ada. So I'll talk about this more next time, but you can design the compiler so that it will be able to more easily support multiple languages. But strictly speaking, no. Each compiler is for each language that you want to support, each input and output program language. Yeah?
Is that why, like, if you download a program, you download the executables, but they basically compile them differently, I guess, depending on the system and architecture you have?
Oh, yeah. So you wouldn't be downloading the executables, you'd be downloading the source code.
Oh, really?
Well, it depends. If you look at like apt or something, or it depends on the system. So like Mac years ago. I think they actually do this now for ARM, but they had so-called, I think, fat binaries, where they would actually ship multiple architectures binaries in the same package, and then it would sort of dynamically pick based on what machine you have. apt and other package managers, you can specify the architecture you want. They support binaries for multiple architectures, and they'll just have the binaries for multiple different architectures available to you. You can also download, you can also build from source. So this tool chain that I showed you, where you do git clone, make, and run, there's additional tooling that will port that source code to a different architecture for you. They're called auto tools or autoconf. Part of the same kind of family of the tool chain. But that, yeah, I thought it was, they talk about it in the book, actually. If you read the C programming book, I think he mentions auto tools in there as well. Yeah.
Are you saying, like, you know how it's written in MIPS?
So MIPS is a machine code for a MIPS processor. So that's kind of on the same level as an x86 architecture. So MIPS, probably few people use a MIPS machine here. And I think you had to emulate it. You needed a virtual machine for it. Most people, in consumer devices at least, have x86 or ARM. But those are all just different processor architectures that have their own definition of the machine instructions. It's kind of like C versus Java. They take different languages. Even though they can compute the same thing, they just take different languages. They take different assembly languages. If that makes sense. Does that make sense? Okay, so we're translating between two languages here, the C program and the Hello program. How do we make sure that it's actually going to execute what we want? So, if you are going to China and you want to be able to communicate with people, you need an interpreter, or you need to hand translate things ahead of time. How do you make sure that you're actually expressing the same thing? Well, the compiler is supposed to make sure that your output program behaves the same way as your input program. But what does that mean? If a C program has a for loop, does assembly language have a for loop construct? No. What do you have in assembly? What you learned, the MIPS or yeah. You have jump. Yeah, you have jump. You can branch. That's not a for statement, right? For loop statement. So what can the compiler do to make sure that the for loop, the behavior of the for loop, is the same, or what does it even mean to have the same behavior in the assembly program? I mean, obviously, each individual instruction is not going to have the same behavior, right? So the for loop can't even be expressed exactly in assembly. So how can we guarantee, or how can we check whether they're the same? Yeah. Yeah, by their output. So one definition of an equivalent program is that a so-called functional equivalence or observational equivalence, that for the same inputs, you get the same output. And that's really all you can do for deterministic programs, because they're different programming languages. How do you make sure that that's the same thing? It's like speaking Chinese or English. The actual words are going to be different, the phonemes are going to be different, but you want to be able to express the same thing. But what about like random programs? Have you ever used rand in like Python or C? How can we make sure that program compiled is the same? Or what even is randomness in a program, in a machine? Yeah.
Isn't it like in most modern things, something like resistance that they're listening for, that kind of makes it pseudo-random?
Okay. So
like that's kind of like an input almost for a program.
Yeah, and that's exactly it. So the program itself, when you call rand, the program itself is deterministic. It's just that the random number generator takes in an input that appears random, or actually may be random if it's generated through some physical process that you could not predict. But the program itself, at least in the architectures we're talking about, are deterministic. That when that CPU, as long as it's designed correctly, whenever it gets the same input, it's going to give you the same output. And randomness is achieved by just passing a new input to your program. And that input may be randomly generated, but given the same random input, your program will behave the same way. There are new architectures, like quantum architectures, which are sort of intrinsically probabilistic. And there are also probabilistic programming languages that actually let you deal with statistical distributions. And so in those, they may not be deterministic, but there still are distributions, like probability distributions that they follow. But for the architectures and languages we're dealing with this class, they're totally deterministic. And so that makes it a little bit easier to validate that the translated program will be the same as the input program, because you just say, well, for any input, you should have the same output. So you could even imagine testing by just generating a whole bunch of inputs and seeing if the outputs are the same. So would that work actually as a way to prove that a compiler is correct? Generate all inputs and generate the outputs? Yeah.
Would you be able to do that with a compiler if you can't execute a text file directly?
Okay, so that's a good point. So how do you run the input program if there's nothing to run it on if you have to compile it? That's one problem. Let's say you were comparing two compilers to make sure they were the same. Would you be able to generate all inputs and check all outputs?
Yeah. Oh, not literally all of them, but like a set of them.
Okay, a set of them, right? So you may not be able to do all of them because there may be an unbounded set of inputs. It may take an unbounded set of strings. And even if you could generate all inputs, there's a famous, well, at least for computers that have infinite memory, there's a famous result by Turing, the Turing halting problem, where he proved that even if you could generate all inputs, you actually wouldn't necessarily be able to prove equivalence of all programs. You wouldn't be able to get the output of all programs, because you could always construct a program that would kind of violate your assumptions, violate your program that tries to prove the equivalence of two programs. Take like a theory of computation class. Maybe it might have to be a graduate class. You can learn about decidability and Turing completeness. So compiler writers have to resort to other techniques. There are formal techniques for proving. You take a model of the input language and the output language, and you can write a proof that the translation actually will be equivalent for all inputs and outputs. That's also kind of outside this class. But so in this class, we'll use testing, and we'll use reason, informal reason, to guarantee that our output is the same as the input. All right, so that's compilers. Questions on kind of the overall concept of a compiler. So let me put the diagram back up. So compilers are translators, and their goal is to translate one program to a program in another language, usually a lower level language, but preserving the equivalence of those programs, preserving functional equivalence, that the same inputs will give you the same outputs in all cases for that program, all cases where the input program is defined. Questions on that? Yeah.
Just like looking at the diagram, does the input also have to be like compiled or at least translated into binary?
No. Well, so this depends on how it's all going to be binary, because the input will eventually reach the CPU. The CPU only works with numbers. But depending, so there's if you take like an electrical engineering class, there's a whole suite of ways, so peripherals for your device that you can give inputs to. So there's cameras and microphones and keyboards, mice. These are all inputs to your machine, and they all ultimately are quantified as numbers that your CPU will process. So no, the input itself doesn't need to be translated.
It's kind of like abstracted in a different set.
It's well, if you think of all inputs as being binary data, then you can define that for hello.c as well. And you can define it for both machines. So you can say that both machines just take binary data, for instance. You could sort of frame it that way. But yeah, that's a good question. Yeah.
So when the compiler executes on the CPU, the input will be the program we are trying to compile.
That's right. Yeah, that's right.
And the output will be the compilable.
That's right. So that's this diagram here, the compiler. So I should have put like compiler.c here. So this is not compiler.c. This is the compiler binary. So to make this, to add a little layer to make this a little even more complicated, your compiler binary is running on the CPU. It's taking your C program as input and giving you an executable as output. But earlier, someone must have, if your compiler is written in C or not in assembly, then somebody must have also taken your compiler program. Sorry, I'm confusing myself here. So it must have taken your compiler program and run it through your compiler to produce the compiler binary. So this is that bootstrapping problem that we talked about before, where the compiler needs to be able to compile itself if you don't want to write the compiler in assembly. So strictly speaking, if I want to use my same CPU diagram here, my compiler gets run on the CPU. The C program is passed as input, and then the compiler binary is the output. So this seems kind of silly, right? Your input is the same, or the thing running is the same as the output. But this is a good way to make sure that your compiler actually works. It also means if you want to modify your compiler or upgrade your compiler, you don't have to go back to scratch and write an assembly program. So this might be something like compiler.c star, and this will be like a modified version of the compiler, or maybe ported to a different architecture. Does that kind of answer your question? Does that make sense? So compiler is a binary that runs on the CPU. It takes the compiler source code as input, produces a compiler binary, and then that compiler binary also runs on the CPU. Takes whatever program you have and runs it and produces the binary. Yeah.
Is there a way to reverse this? So you give it a binary file and gives you like a C program?
That's called decompilation. And yeah, there are tools to do that. There are tools that will do that. Yeah. Also a little outside the scope of this class, but yeah. This is used for like security analysis, reverse engineering tools to try to figure out, recover the source code. There are, I think, video game producers who want to like get emulators who want to get the source code of the original program. They'll use decompilers. But yes, there are decompilers that will go the other way. Now, you lose a lot of information, as we'll see when we talk about compilers. You lose a lot of information about like names, what original construct were used. The compiler does optimizations that'll make it hard to tell whether you had a for loop or a while loop, for instance. But yeah, there are tools that attempt to do this, but they're like trying to infer the original source code. They won't necessarily give you the exact source code. Yeah.
What kind of courses that is it provided? What course does it provide that will kind of go over that?
Decompiling or compiling?
Both, kind of.
So I have a little add in here for my course. I have a course on compilers. Where do I have it? So you can take this class. It's a graduate course, but undergraduates can take it. I think programming languages is a prerequisite. But I teach this every spring so far. So if you want to actually get into the weeds in compiler construction, you can take this class. I teach it, and teach it. Should be every spring I teach it. All right, so that's the joy of compilers, and hopefully you can kind of look at these diagrams a little bit, or try for yourself. You can actually build GCC if you really want. It's a big program to build. But if you can wrap your head around this kind of self-referential aspect of compilers, then it'll make it a little easier for you. And also, even just looking at this diagram, when we go to write our compiler, just be aware that we've got the input program, the output program, and the compiler program itself. You'll be writing the compiler program. And your compiler program will take input programs and produce assembly code. So you gotta, these are all gonna be in different languages. So you just have to keep in your head the difference between the input program and the compiler. And remember, the compiler is not interpreting. It's not trying to give you the answer for the input program. It's just trying to translate it into a new version of that program, a new implementation of that program. But we'll get to that when we get into the compilers. That's the confusing part, is to resist the urge to start writing an interpreter, because that's kind of like naturally what you want to do. You like read in arithmetic, and then you're like, well, hey, I have arithmetic in my language, so I'm just going to run arithmetic. I'm going to run plus. But that's not what a compiler does. That's an interpreter. Okay, so an interpreter, and I struggled to find the right terms for this, but an interpreter effectively simulates the actions of the source instructions. So if you think of your processor as an interpreter, the machine instructions are just invented by some electrical engineer. There's no physical thing in the world that will run that. So what they do is they build a circuit that will give you the output of that human-defined machine. So addition, there's nothing intrinsic really about addition in a circuit, but you can design a circuit that will do addition for you. We have a notion of addition. There are sort of metamatheticians who try to axiomatize what addition is. But if you just define addition on paper as an operation itself, then you can design a circuit that will give you the output of addition that you want. So in the machine level, this is implemented in hardware. But you can also implement a software interpreter. So does anyone know interpreted some languages that have interpreters? Yeah. JavaScript, Python. Yeah, so these are interpreted languages. And in reality, they actually use a mix, pretty much all programming languages use a mix of compilation and interpretation. Python actually compiles to a smaller language. But if we pretend that Python is purely interpreted, the interpreter will read in, kind of like your MySH interpreter, which is a command line interpreter. It'll read in each line of that Python program, and it'll run code. When it sees that, it'll see an addition, it'll run code to perform that addition and give you whatever the output of the program is supposed to be. Yeah?
This interpreter uses the executable or the program?
So let me diagram it to show the difference between a compiler and interpreter. So an interpreter, let me do the overall diagram and then we'll see how the machine fits in here. So my interpreter takes in, let's say it's Python, it takes in my Python program and it also takes in the input. So the interpreter takes in the input, just like our CPU. You can think of the machine as taking in the input and then produces the output. So if we use another kind of CPU view of this, the CPU is taking, so let's put aside the CPU version of this for a second because actually this Python program is also let's do this. So the interpreter itself, it is a binary program. You have to compile the interpreter if you write the interpreter in anything other than an assembly language. And the machine is also taking in the Python program and it's taking in the input. Ultimately, the interpreter is directing the machine to take in that input and giving you the output. So this is kind of the way oversimplified view of the interpreter in terms of the processor. But this is really the kind of canonical diagram of an interpreter. The interpreter program takes in both the source code and whatever input you have to the program, and it produces the output for you. Yeah?
It doesn't work with C program.
Well, so C, it could. You could write a C program interpreter. So this is kind of like a question about whether languages are intrinsically compiled or interpreted. And strictly speaking, they're not. You could write an interpreter or a compiler for any language. You could compile Python to C or assembly or to C, which some people do. You could write an interpreter for C if you wanted. It may not be, you'd have to model the machine in your interpreter. But the language itself, there's nothing really intrinsic in the language that makes it compiled or interpreted. You could write a compiler or interpreter for either one. But some languages have features that are more convenient for compilation or interpretation. So C, for instance, doesn't define the bit width of integers. Instead, it just leaves it up to the machine. Leaves it up to the, it defines out of bounds as undefined behavior, so it ends up being kind of left to the machine to try to catch those kind of things. Yeah?
So the biggest difference is the creation of the executable?
One way you could say that, yeah. That is the main difference, is that the compiler creates an executable that will run on the processor, whereas the interpreter, that never happens. You never create an executable in an interpreted implementation. The interpreter reads the instructions of the interpreted language and directly executes them or simulates their behavior. Yeah?
So when people talk about just-in-time compilation, is this the same sort of thing?
So just-in-time compilation is one of these. So compilation and interpretation are actually generally blended in most programming languages. So just-in-time compilation is a technique for improving the performance of interpreted languages by compiling on the fly commonly used traces through the program, commonly used paths through the program. So that's just-in-time compilation. So these techniques are really actually blended in most programming language implementations. But yeah, I think what your fellow student said, if your programming language implementation produces a machine code binary, then you can call it compiled. if it gives you the output when you run it, we can call it interpreted. That's like kind of a simplification. All right, let's see an example of a couple of these. So let me actually write some code here. Or actually, for the sake of time, let me just go through the code. Okay, so here is an example. So let's say we want to translate 1 plus 2 to machine code. So this is a string, and I want to write a little calculator program. So first of all, if I take this string and I somehow, put it in memory and point my program counter to it and have my x86 architecture machine start running it, what'll happen? Well, I get 3 as the output. Can I execute this string, 1 plus 2, on, say, an x86 processor? Kind of a subtle question, right? Because you keep thinking in your head, well, yeah, it can do addition. But remember, the input to this is literally a string. And yeah, go ahead.
If it wasn't a string, wouldn't 1 and 2 be like 2 separate variables and not an instruction?
If it wasn't a string, right? But it is. And your Hello World program, those are strings, right? And you don't write like the Intel mnemonic for addition. You write the plus symbol. So what is the plus symbol in a string in our editor? What is it? Yeah.
It'd probably be like an ASCII character.
It's ASCII code, right?
Yeah.
And if you look at the ASCII code for numbers, like 1, it's not the number 1. It's not binary 1. It's like, I forget which one it is, 49 in decimal. So the ASCII code for the symbol number 1 is decimal 49. So if you actually open up your Hello World text file and look at the binary of it, it is in no way reflective of machine code integers or addition. And the plus symbol is definitely not, as far as I know, anywhere close to so this is, they represent it in a different way, but, it's decimal 43 for the plus symbol. I'm pretty sure that does not correspond to the Intel instruction for addition. So this string is a completely different representation from addition in your machine. And that's where the compiler comes in. The compiler takes this representation, which no machine that I know of will directly interpret, and it converts it into machine code. So here's a really little simple calculator program. So what does it do? It reads in 1 character, and it says, well, okay, the first character is going to be the left operator, or operand, of my operation. The next character I read in is going to be the operator, and the next character after that is going to be the right operand. And so this is kind of like the little definition of your language, because this is enforcing how the programmer is supposed to give or write your language. So this implies that you have to give a character in ASCII, followed by an operator, followed by another character for an integer. With me so far? Just reading in these 3 characters from the input? Questions on this code? Okay, and so this is the compilation step. We look at what kind of operator we have. So here we actually check whether it's the plus symbol. And if it is, we generate machine code. We generate machine code that we hope is equivalent. Now, there's nothing telling us whether it's equivalent. We have to prove that. But how do we do addition in assembly? Remember in MIPS or x86, whatever you like. Yeah. Go ahead.
ALUs.
What's that?
ALUs.
Well, that's the name of the machine that does it. What's the instruction? Yeah.
So for instance, it would be like add I, and then what the destination, the variable that you're adding, and then an immediate, which would be a constant.
Yeah, there's several instructions for doing it. There's like multiple instructions. But this is one way to do addition in the Intel world. There are several instructions to do this, but you could move immediate. So we'll go over the Intel AT&T syntax, which is what this is. The source is on the left, the destination is on the right, but this is move immediate, the number 1 into the A register, move immediate, the number 2 into the B register, and then call the add instruction, which stores the result in the A instruction. So this is an Intel assembly version of this input program. As long as we're kind of assuming what the definition of plus is, which can't necessarily take for granted. You could write a language where the slash symbol is for plus, if you like, because it's just ASCII code. There's nothing intrinsic about the symbol that makes it addition. It's just a symbol. It's this interpreter or this translator that gives it meaning. But this is what the output we'd want to see. Make sense? So do you agree that if we kind of take for granted that this is a calculator where we use ASCII symbols for the arithmetic operations, then this is an equivalent output of that program, right? Make sense? Questions on why these would be equivalent? Okay, so then the challenge becomes, how do we take any input? Let's say our language is single-digit character, an operator, single-digit number. Well, we could use a little template here for this assembly output. So this is a little bit of annoying, printf formatting, but basically I say, all right, take whatever character I have in the left variable, take whatever character I have in the right variable, and generate move instructions. And then, if it's a plus operator, then generate the add assembly instruction. Questions on that code? Does that kind of make sense? So we have our first actually kind of compiler here, where we're translating what is just ASCII code, which has no meaning to the machine, has meaning to us because we're interpreting it in our head. We have the semantics of these symbols in our head. And then we're automatically generating assembly code that assembly code will change depending on what our input is. And as long as we've done this correctly, we'll always get an equivalent assembly code program for whatever input we give it within the definition of our language. And so here's our program, so I can give it I don't think I did other operators, but you can see this program will generate, if you give it other numbers, it'll just it's like a template. It'll just plug in whatever number you gave it for the left and right operands. But if you run this, it should give you the same output that we would expect from our intuitive definition of this input language. All right, questions on this? So here's our very first compiler we see in this class. Pretty straightforward, right? So as long as you get the idea that this program is not meant to perform the addition, it's just meant to generate another program. It's really a code generator. It's generating assembly code, but it's supposed to be equivalent to the input program. And without any formal definition of the input language, it is this program that actually defines the meaning of it. So it's defining the meaning of the input program in terms of how it generates output, assembly code output. Questions on this? If you can wrap your head around this, try writing it yourself. If you can wrap your head around this, you'll get the kind of crux of compilers. Yeah? That's a good question. Why do we have so many programming languages if it's all assembly? That's kind of a question for like a programming language class. There are features in languages that make programming languages convenient for certain tasks. So C has no object orientation, but if you learn C++ or Java, there's some utility to be able to express more coarse-grained computational constructs or lay out memory in more sophisticated ways. So if you take a programming language class, the main goal of programming language design is to provide methods of abstraction for the user. So you could even ask, to kind of reductio ad absurdum to your question, why even have a programming language? Just program in assembly, right? Why not just program in assembly? Why bother using C? If you're really good at assembly program, it might not take forever. But assembly program doesn't even have functions. So C provides functions in the way I'm going to define them in a couple lectures, but it divides functions. C and the machine don't have functions. So wrapping your code up with local variables, this feature gets added by the programming language, and the programming language translation or interpreter or translator for translating machine code implements equivalent code to that abstraction. So that's to kind of give you a lazy answer. It gives you methods of abstraction, and those supposedly make coding easier or harder. They can also provide ways to check the program for you automatically. So C will do type checking to make sure you're using the right kind of variable in the right context. But yeah, that's a really good question. Yeah.
Why do we use C instead of like more powerful programming languages like why do we use like filters?
Why do we use C? So this is really an engineering choice. If you ask like Linus Torvalds why Linux is in C, he has very strong opinions about C++ and other languages. Some languages, so I view programming language choice as an engineering decision where you pick the right tool for the job. So you'll see on Stack Overflow people saying this is the best language, this is the worst language. My opinion, it's really an engineering choice. You make an engineering decision about what's going to be the best tool for the job. And sometimes, unfortunately, that means legacy code, dealing with legacy code. So C has probably billions of lines of code, hundreds of millions that you're like running, or not running, but hundreds of lines of code that generated programs that you are probably running right now on your machine. And there's a huge amount of legacy code that still exists for these languages. So I would say it's a choice that goes beyond technical decisions. But even in the technical decisions, there are choices, engineering choices about language design. So performance of the language, ease of programming, how your developers are trained. But this is also kind of outside the scope of this class. But yeah, that's the short answer, I would say. All right, other questions about our first little compiler here? Okay, let's take a look at the interpreted version of this program. So it starts the same way. We need to process the input language. We need to read in the input language. So we just read in the left, right operands and the operator. But in this version of the program, we first convert the ASCII into the number representation that our interpreter language supports. And there are many ways you could do this. This is my lazy way of converting ASCII into an integer in C. The reason this works is because you can actually subtract. Characters are just integers in C. You can actually subtract them. So if you take whatever the ASCII code for 0 is, subtract it from the ASCII code for any other number, you get that number because they're all in sequence from 0 to 9. Yeah?
Is this assuming that we don't put actual letters by the head like this one? But actually, we can go to A plus B. Or assuming we won't do that?
Yeah, that's a good point. So I'm really glossing over the definition of the language here, but all this language can take in and correctly translate, even though there's no explicit definition of it, is it can only take in 3 single characters. The first and last character are supposed to be an ASCII representation of a digit, and the middle character is supposed to be the ASCII representation of an operator. So that's kind of our definition of language, and I glossed over defining it. I just kind of took for granted that you would get it. But yes, that is a restriction on this language because of how we process the input, how we process the string input. Does that kind of make sense? So what does our interpreter do? We convert it into a representation that the language we're writing in represents integers in. And then we just literally perform the addition in C. We use our C notion of addition to perform the addition. It almost seems like tautological, right? Like we're reading in a plus symbol, why do we bother having to turn it into a plus symbol? But if you run this, you'll get the same output that you'd get for the compiled version for a correct set of inputs. So here, 5 plus 3, 5 and 3 get converted into the machine representation of integers because that's how we wrote our C program. And then the result is adding those two numbers together and printing them out. And so this is the output of our interpreter. Questions on our first interpreter implementation? I'm sure you can see all sorts of problems with these and limitations, but yeah.
Is the reason that interpreters tend to be slower because the interpreter itself has to compile?
It's not the interpreter compiles, it's just that I think architecture is so much faster at running its instructions that, without techniques like JIT, just-in-time compilation, I don't really know the latest results on performance, but I think it's just because hardware is so much faster than software because the software is running on the hardware. You also have memory and other types of pressures that are causing performance changes. But I don't know the exact latest results. But typically, the kind of common wisdom is that you're running on the bare metal on the architecture versus running software that's trying to interpret that language. All right, any questions on our interpreter? So this is kind of a silly looking interpreter because we're actually using the same symbol in our input language and in our compiler. So let me show a example of using an operation that isn't in C to kind of show where an interpreter will really differ from a compiler. So if we have a operation that doesn't exist in our language that we're writing the interpreter in, then we're going to need to simulate the behavior of that operation, of that operator. So here's the pseudocode for what that would look like. We'd read in, the operands and the operator, and here's one algorithm for computing. So this is supposed to be power exponent. So this is one algorithm for computing that, right? It's just repeated multiplication. You just loop over 1 to the right operand and perform the multiplication of the left operand multiple times. Questions on this algorithm? This is how you implement power, because I think most processors don't have exponents, I don't think. Questions on this? So hopefully, I have like a full program you can see in the notes, and you can go over and see. I have a little implementation of the assembly for power. It just implements that same pseudocode. So this is what it would look like. One way to implement an assembly, and here's the interpreter version. All right, questions on compilers versus interpreters and their implementation. So super basic intro. Just remember that compilers translate to a language that's going to be interpreted by the machine, whereas interpreters do that simulation of the input language on the fly as it reads in each line of code and produces the output. Yeah?
Is there a practical reason for which, when you were saying that decompiling would load some data, the names are understandable, the names are very good. But what about for loop and while, for example? Why wouldn't they be two different instructions?
So for and while neither of those are machine instructions. They are C code instructions. And both of them are implemented without optimization. Both of them are implemented using jump and branch. So you could look at the pattern of the assembly code and try to guess that this must have been generated from a for loop. But you just might not be right. It might have been a while loop that looked very much like a for loop.
Is there a practical reason that it is implemented that way?
It doesn't. So it doesn't have to be implemented with jumps. So there's all sorts of techniques like loop unrolling, or if the compiler can figure out how many times the loop runs, it can avoid using a jump. So this is again kind of getting into like the compiler, bigger picture of the compiler. But there are many ways to translate programs to equivalent programs. There's not just one equivalent program. Even in C, you could write a for loop and a while loop and implement the same program with two different C programs. So same when you translate to assembly. There are many different ways to translate it. But there are kind of easy ways to do it, or easier ways for certain constructs that allow you to do this very easy template approach. And typically modern compilers are implemented by having the most naive, simple way of the translating and then optimizing later to have a more performant implementation, rather than having the first step of the compiler try to translate to the best assembly code. Instead, they translate to the simplest version of each construct and then do later optimization to improve performance or change the behavior of change the implementation of the assembly. I don't know if does that answer your question? Sort of?
Yeah.
So basically, there's more than one way to skin a cat. There's many assembly versions of the C program that will be equivalent in the sense that they'll have the same output. So for instance, I could, instead of addition, I could do subtraction. I could negate the number and then do subtraction. And that would be an equivalent program, but it would have a different sequence of instructions. Okay, so we'll get more into compilers. We'll actually build a small compiler in this class. But I also want to get to, again, just a little ad for my class. If you're interested in this compiler stuff and want to learn more about this, I teach a class on this. This is the graduate class, but undergraduates can take it. I think programming languages and something else, maybe CS2 or discrete maybe, is a prerequisite, but undergraduates are free to take, I think up to 3 graduate courses. So if you really, really like this stuff and you really want to get in the weeds with it, take that class. Okay, so let's actually, so that's the programming language part. Let's look at the whole flow from source code to running program. And each one of these has a tool associated with it that will take your source code into a running program. All right, so the C program is first run through the C preprocessor. I don't have time to get too much into this. I do some research working on this, but this is basically processing your includes, headers, your macros. Then we get a C program, a pure C program. This gets compiled by GCC into an assembly program. So before it reaches an executable, it gets turned into assembly code. And then that assembly code gets turned into what's called an object file. This is just a fragment of a program. This is machine code, but it's not yet an executable yet. And then this machine code gets joined together with other machine code that turns it into an executable file that can then be run on your operating system. And the kernel will take that executable file and turn it into a running program in the manner that we described, using fork exec, as we described earlier in this class. So the C preprocessor produces C code. The C code turns into assembly. Assembly turns into machine code. The linker combines the machine code with other code necessary for running. And then execve takes this executable file, loads it into memory, and that's when you get your running program. So questions on the big picture of this? Yeah.
Yeah, or what kind of additional code that comes from linker?
Okay, let's take a look at it. So let me show you each of the instructions that let's look at the output of all of these. Okay, so let me just show this here. All right, so let's take a Hello World program. As usual. All right, here's our Hello World program. So I'll just confirm that that's here. Here's our Hello World program. Now let's run the preprocessor. Preprocessor gives you .i files. -e runs the preprocessor. So this is what your program looks like after running the preprocessor. It's hundreds of lines of code with lots and lots of definitions. At the very bottom, here is our body. Here's our main method. And what the preprocessor does is it resolves, among other things, this include. So this include is not really part of the C language proper. It's part of the preprocessor language, which we'll talk about this a little more when we get into our assembly code. But it gives you all of the definitions, like printf. Gives you declarations of all those, because without those, the compiler would not know about that function name. So the first step turns your little 10-line program into a many 100-line program that has a ton of just declarations of library calls. So that's what the preprocessor does. The next step is the compiler. So if we use -s, we can actually tell the compiler. So what the compiler will do is it'll run all of these phases up to executable. GCC will by default run all of these tools for you behind the scenes. But in reality, if we separate these steps out, decompose these steps, we can see what the output looks at each phase. So the actual compilation part, if we compile the preprocess, the .i file is now like pure C. we can compile this to its assembly code version, just like we did in our compiler. So let's take a look at the assembly code. And so this, I don't know how familiar this will look coming from MIPS, but these are the mnemonics for x86 assembly code. And you can see we've got move, we have load, we have call, move. So same kind of instructions you would have seen in MIPS, pop. There's a lot of extra declaration stuff here that you don't need to worry about. But you can see here that our basic Hello World program is being turned into an equivalent assembly program. Here's the string. This is basically saying put the string in memory, and then it's actually loading the argument into a register and then calling actually in this case, it's the compiler turned it into put s instead of printf, but put s is just another library call that will print a string. But there's our equivalent assembly code. Questions on that? Kind of makes sense, right? So we've preprocessed, we've assembled, and now let's get into what object files versus executables are. So to create an object file, this is the -c command. Let me make sure I'm not wrong. So -c will do an object file. So if you remember from the makefile lecture, we use -c to do an object file. So we can't actually, the object file is going to be now machine code. So we won't be able to view it in a text editor. It's going to look like gobbledygook to us. But there's a tool we can use called object dump, which dumps object files. And we can actually, with -d, we can disassemble it. So it's going to look very much like the assembly code, because the assembly code is almost a one-to-one mapping to machine code. So if we disassemble it, if we had to look at it in binary, I don't know the actual Intel ISA like in binary, but we can disassemble it back into assembly mnemonics, and you can see it's it's the same basically the same stuff here. We're loading the hello world string into memory and calling some address here. So we lost that put s name in this assembly code, but this is the same same kind of code we saw with hello s. But now it's in binary. So if you actually look at the hex of this, it's not ASCII code. It's not text readable. It's not ASCII readable. Okay, so there's our object code. To see the difference between object files and executable files, we have to know a little bit about what linking does. So let me first link this. So unfortunately, we lost a lecture on functions and the C runtime, which we'll have to make up for next time. But I'll try to explain this quickly here. So this LD instruction, even though it's misnamed as a loader, it's actually the linker. And what the linker does is it takes multiple object files, hello.c, hello.o, and any other files you might have. So you could even have like standard I/O in the old days. And it takes these multiple object files into the linker, and it produces your executable file. Let's call it hello.elf or hello.exe in the Windows world. So it just takes multiple compiled C programs, and it joins them together into a single program. So when we talked about makefiles, we did separate compilation. We talked about separate compilation where you break your program down into multiple source files. In the C world, you compile each of those individually into machine code and then join them together into an executable. Yeah, what's your question?
Is it just concatenation or is it doing something?
So that's a very good question. So it's not just concatenation. So let's say we've got a call to a function. So there's our linker. We produced this object file here. Or sorry, our executable. So this is our executable. It has a lot more. So here's our main, but this has a lot more code in it now that we've linked. So we've linked it together with several other compiled programs. But the reason it's different from just literally concatenating the code is because of branching. So for instance, in our Hello World object code, we had a call to this function putS. But putS was never defined in our program, right? We never defined putS or whatever, or printf, or any of these other functions that you call. You just call them, and magically through compilation, that function is now available in your executable. So what linking also does is it resolves function calls with their actual definitions of the function calls. So if we look inside of the executable, so this is the object code. If we look at the table, the function call table in the executable, we'll see that now putS, oh, okay, so this is because of dynamic linking, but let me, so this is going to call a, where's the actual function? So this is going to, so this is easier to show with, let's see. Let me show this very quickly with an example to show you, because this is really the last step. So I'm just going to call one function here. I'm not going to define it, I'm just going to call it. And I'm going to define the callee here. The callee is just going to return something. So I'll just compile both of these programs. Where am I? Oh, I'm in the wrong spot. Okay, so I've compiled these two programs, callee and caller. If we look at what functions are defined in these two programs, you'll see in one we have a call to the function callee, and there's no address of it. The code for it is not in our machine, in our code here. It only has the function caller. Whereas callee, this other file, has the definition of it. So what the linker does, in addition to just concatenating the code, is it links up, it combines these two programs into a single binary. So let me put a main method here so that I can link them. So if I ask GCC to compile and link these into main, you'll see that now callee and caller are both defined in this executable. So the linker doesn't just concatenate them together, it also works out function calls. It also works with dynamic linking, which is I have reading material if you want to learn about that, and also works out branching and locations of memory. So the linker is what takes all of your separately compiled programs, turns it into an executable. Also importantly, gives you the it also gives you the C runtime, which I didn't have time to cover last time because we lost the class. But the C runtime is actually what interfaces with the operating system. When your program gets run, the kernel by default will actually call this function, the start function, _ start function, and that's what calls main. It does a little setup like passing in argv and stuff like that. So the C runtime does a little setup for you and then calls main for you, but the kernel actually calls start. So this is the loader. When the loader runs this program, it loads all of this into memory, it looks at the table, and it calls start. And it's the C runtime, which we linked here in our loader step, this C runtime, this CRT1, this is what actually calls main for you. It's a separate special program that you link with every C program in order to have main get executed with all the information that you expect it to be executed with. So that is how your program, your source program, through many series of steps that we all take for granted because we just run GCC and all of it gets turned into a running program. C preprocessor resolves includes macros. The compiler turns it into assembly. The assembler turns it into machine code. The linker combines machine code into an executable with the right runtime and right behavior for the loader. And then the loader goes into start, and that's what kicks off actually running your executable. All right, so there you go. If you want to read more. Oh, yeah, question, please.
Back to the diagram.
Yeah.
If you're like third error, any of the steps, will it give you an error?
Oh, yeah, GCC will give you an error. This is why GCC errors are a little confusing because they may be at different steps. So you may have a preprocessor error, you may have a GCC error, you may have a linker error, like if you miss main. And so the error is just given to you, and you don't. They give you a little prefix to say loader error or preprocessor error. But yes, the error will just come from whatever stage you have the error in. And that actually explains why you have errors at different phases. That might be confusing. Okay, so if you want to read more about, like, there's a whole bunch of material here, practical material, like from OS Dev, from the Linux news magazine. But yeah, you can read about the runtime, read about how programs get run. Anyway, have a good one. Exam next time, don't forget, and I'll see you all next time.